Hello everyone, and thank you for your attending. My name is Jin Yu, and today I'm excited to share our recent work titled A Multimodal Multi-Agent Framework for Radiology Report Generation. Here is the outline of our presentation. First, I will start with the background information to provide the context and motivation for this work. Then I will go with the related work to explain the existing approach and multi-language models. After that, I will explain our methodology part, including the overview of our framework and the implementation details. And next, I will present the result and analyze part to show how our approach performs compared to other baselines. And I will also include the ablation study to demonstrate the impact of the different components in our frameworks. And finally, I will finish with the conclusion part. For the motivation part, our main objective is to improve the quality of radiology report generations, or RRG. RRG mirrors the clinical workflows that doctors follow, like the step-by-step reasoning and documentation. So the structured process can actually be simulated using the multiple intelligent agents, and each agent will be responsible for the different stages of the clinical pipeline. And the most important thing is with the rapid growth of the multi-large language model and large language models, now we have the powerful tools that can help us significantly improve the efficiency and the accuracy of our process. And here are some challenges in the existing methods, like some limitation of some multi-language model. Here is a cross-model misalignment, like the misunderstanding when we transforming the image information to text, and the hallucination, the classical issue in large language model domain. The model sometimes will give us an answer that look really nice but incorrect. And if we only rely on a single model, it will lack the control and flexibility, and a single multi-language model is often not enough to handle all the subtasks for RRG. And here is the related work. So there are already some work in the multi-language model for radiology report generation, like the R2 general GPT, X-ray GPT, and so on. They usually combine the vision decoder and the language model. The vision decoder are used to extract the image information, and the large language model are used to generate the text from the image. However, the single model architecture can't meet all the requirements in the RRG domain. Next, continue with the retrieval augmented generation, or the RAG. RAG can enhance the accuracy of the medical text generation by connecting the model's outputs with the external knowledge database. This approach helps us reduce the hallucinations and fill in knowledge gaps. This is especially important in the medical domain. However, there is a key limitation here. Current RAG framework only supports the text retrieval. That means they can't help us deal with the visual or multimodal information. And here comes our methodology part. We designed a multimodal and multi-agent framework for radiology report generation, the RRG, and rather than relying only on a single multi-language models, we divided the task into 5 specialized agents, and each agent will be responsible for a separate task. For example, some will be responsible for the described image, and some will for the find the relevant report in the RAG database, and some will for the generate the preliminary report based on the retrieval reports, and some will help us extract the key finding from the existing text information and to help us generate the final report. Here is an overview of our framework. We divide it into 5 agents: the retrieval agent, the draft agent, the refiner agent, the version agent, and the standardized agent. And in the retrieval agent, we combine the RAG technique and the open clip model. We apply the open clip model to read the image information and use the semantic similarity to find the top key retrieval most relevant report in the RAG knowledge database. And in the draft agent, we apply the GPT-4o to generate the preliminary radiology report based on the top K most similar reports from the retrieval agent. And in the refiner agent, we also apply the GPT-4o to extract the key findings from the preliminary report and the top K most similar report from the retrieval agent. And in the vision agent, we apply the LavaMed to extract the visual description. And in the standardized agent, we apply the GPT-01, the reasoning model to generate the final report based on this information above here. And here is a workflow. So we input the X-ray image here, and from inputting the retrieval agent, I use the RAG techniques to find the top K relevant reports here, and then we use draft agent to generate the preliminary report from the top K relevant report. Use GPT-4o, and in the refiner agent, we also use GPT-4o to extract the key findings from the top K relevant reports as a preliminary report. And at the same time, we input the X-ray image in the vision agent. We use LavaMed to extract the image information, and generate the visual description about this X-ray image. And at the next step, we apply GPT-01, the most powerful reasoning model, to combine all the information we have: the preliminary report from the retrieval agent, the key findings extract from the refiner agent, and the visual description from the vision agent, and to generate the final report. And here is a case study using our framework. Here is the original image and the original report. The vision agent and the retrieval agent is to separate and parallelize process. So we input this image into the vision agent. Use the LavaMed will give us a visual description like that. And in the retrieval agent, we use RAG techniques and the open clip model to help us find the most similar top K retrieval reports in the RAG database. And in the draft agent, we use GPT-4o to generate the preliminary report like that from the top K retrieval report here to generate the preliminary report. And in the refiner agent, we also use GPT-4o to extract the key finding from the draft agent and the retrieval agent. And the standardized agent, we use the reasoning model, the GPT-01, to generate the final report and combine all the information we have: the visual description from the vision agent, and the top key and the draft agent, and the preliminary report from the draft agent, and the key finding from the refiner agent. We combine all the information we have and generate the final report. Here comes the dataset and preprocessing. We use 2 datasets in our framework: the MIMIC and the IU X-ray. The MIMIC will use to train the retrieval agent. We select 3,000 image report pairs from the whole dataset and use the small sub dataset to fine-tuning OpenClip to make the OpenClip better adapt to radiology image domain. We aim to improve the semantic relevance of the retrieval reports. And for this study, we use the IU X-ray dataset to evaluate our multi-agent framework. Specifically, we selected 2,068 training samples to build the retrieval database for our RAG component. These samples will use as a reference case to support the RAG system, and then we use the other 590 text samples to evaluate the quality of our generated report results. This test set helps us assess how well the system performs under the unseen case. And for the evaluation metrics, we apply two kinds of evaluation metrics. First is the automated evaluation matrix. So we compute the similarity, the semantic similarity between the final generated report and the original report. We compute the blue, rouge, mentor, and the burst score between the final GPT-01 generated report and original reports. So these objective metrics are used in our tasks to evaluate the similarity between the final report and the original report. And for the second way, apply the large language model as a charge evaluation. We adopt another large language model, the Cloud3 Ops, as a large language model-based human evaluate to access the semantic quality and the value of the final generated reports. So the evaluation metrics will cover the following 5 dimensions, and from 1 to 10, from the consistency and the key finding coverage, the diagnosis accuracy, the style alignment, and the consistency. And here is the result and analyze. First is the quantitative analysis. So we compare our multimodal and multi-agent frameworks with SOTA medical multimodal large language models. Is like the CHEX agent, the mini GPT med, the lava med, and the last is our framework. So we can see our framework get the highest blue, rouge, mentor, and the burst score. All the evaluation metrics we get the higher score. So we can see we get the highest blue like the 00522, the highest rouge 03642, and the row 2 whatever, we get the highest score in all the metrics. And here is the result of the large language model as charge. In this part, we presented a quantitative evaluations where a large language model acts as a judge. Specifically, we use Cloud3 Ops as an evaluation model to rate the generated report across 5 dimensions: the findings, the consistency, the diagnosis, the style, and the consistence. As shown in the table, our method outperformed LavaMed in 4 out of 5 categories. We achieved a higher score in finding, diagnosis, style, and consistence. Although the LavaMed scored better in consistencies, the difference is very small. This proves that our multi-agent framework can produce a radiology report that are more accurate. So our proposed multimodal framework outperforms all the baseline models and across all the evaluation metrics, like the rouge, blue, burst score, mentor. So this proves our framework has a better performance than owning a single large language models. And at the same time, we apply the Cloud3 Ops to perform a subjective evaluation of the report quality. And our method achieved a higher score in the 4 out of 5 dimensions. To test the contribution of each agent, we did the application study. We designed 3 settings, and each has the synchronous agent to generate the final report. From this workflow, we can see the retrieval agent and the vision agent. To generate the preliminary report as a visual description is actually the 2 separate and parallel processes. As the key finding was generated by the refiner agent is based on the preliminary report and the top key retrieval report. So actually, we designed three settings to test each contribution of the three parts: the primary report, the key findings, and the visual description. So each setting will include the Sunrise agent to generate the final report. So the first setting is only includes the vision agent and the Sunrise agent. And the second setting combines the vision agent, retrieval agent, the draft agent, and the Sunrise agent to generate the report. And the last setting will combine all the 5 agents with the whole framework to generate the final report. And we can see the whole framework gets the best performance from across all the metrics: the blue, road 1, road 2, road air, and the mentor, and the burst score. Our experiment result from the ablation studies prove that relying only on the vision input is of course not enough, because the result of the vision agent and the Sunrise agent is actually very bad. And then we combine the retrieval agent and the draft agent. This will significantly improve the performance. That means the text from the RAG techniques from the retrieval database in the IUX3 is actually help us a lot. And at the last step, the additional of the refiner agent, the key finding extra by the refiner agent, further enhance the semantic accuracy and the report quality. And then is the conclusion part. So our paper proposed a multimodal and multi-agent framework for the radiology report generation, the RRG, by decomposing the whole task into five specialized agents: retrieval, draft, refine, visual, and Sunrise agent. Our framework enhances both consistency and the semantic similarity and the performance in the AI-generated RRG report. And the experiment results showed our proposed system outperformed the strong baseline in the both automatic matrix and the large language model as charge-based evaluations. So through the ablation study analysis, we confirmed that each agent contributes meaningfully to improve the quality of the final reports and to improve the performance of the AI-generated RRG. And for the future work, we will explore more robust agent communication and alignment strategies to further improve the performance of the multimodal large language model generated radiology report generations. And in future work, we plan to improve the radiologist expert to help us evaluate of our framework and the generated reports. That's all. Thank you. Have a nice day.